Okay, we're going to start section 2.2. You should have already completed your homework after the chapter 1 test, and therefore you should have completed section 2.1, which is a beginning look at limits, and as you can see, we are going to continue to look at limits in this section. So this is section 2.2, graphical and algebraic approaches to the definition of limits. This is our formal definition of a limit. Let me read it through with you, and then I'll give you time to write it down. L is the limit of f of x as x approaches c, if and only if, for any number epsilon, this is the Greek letter epsilon, greater than 0, no matter how small, so epsilon is going to be a very tiny number. You can see how that comes into our definition of a limit. There is a number delta. I know you're used to the capital letter delta, but this is the lowercase delta. There is a number delta greater than 0 such that if x is within delta units of c, but x does not equal c, then f of x is within epsilon units of L. So you can see that our x value goes with our delta, and our y value, or f of x, goes with our epsilon. Take a minute and write this down. Okay, moving on, I'm going to show you on a graph what these all mean. So if I have a function, f of x, and it is on a particular graph, and I'm just going to draw a little portion of it, and I have some things like this happening. And if I place my x value here, then I should be able to find a limit. So looking at our definition, if L is the limit of the function as x approaches c, I'm sorry, I should make this my c value the way the book has this written, then for any number epsilon, no matter how small, and remember our epsilon is our x value. So what they're saying is that there is some distance that I can go on either side of my x or c value, and we're going to call that distance epsilon. And if I keep epsilon little, and I look at the graph, just this portion of the graph, then if I go along my y-axis, there is a number delta, and you can see it's not exactly the same, but the distance from here to here that will be within, that the limit will remain within. I'm sorry, I kind of misspoke there, but let me show you again. The idea here is that no matter how small I make the space on either side of either my x value or my limit, the two numbers, the x value and the y value, will be within the bounds. And no matter how much I bring this value in close to the limit, no matter how small I make these epsilon and delta distances, the x and the limit remain within those bounds. Now you can see that with the portion over here, if this is a different x value, and I should have really made this a little lower so that we weren't bumping into the other. Let me do some erasing here, because it looks like my limit is almost the same. So if let's just bring this down a bit. Okay, that'll help. So here's the limit for this. And again, if I take and make a distance on either side of x, and if I go up, the problem that happens here is that now, even though it looks like coming from this side that my limit should be here, when I do this with the graph, look what happens. Now my dotted lines are way up here. This is not where my limit is. Therefore, there is no limit at this particular value of x. We'll talk more about that in a moment. But that's the general idea. The epsilons are the distances that we travel on either side of my x value, so it's the distance from here to here. And the deltas, I wrote this backwards. These are the deltas. These are the epsilons. I apologize. Fix your paper. Delta is the x distance, and epsilon is the y distance. I apologize. Go back and fix your notes there. We got it right on the definition. X is delta, y is epsilon. I put it wrong on the graph. So fix your demonstration and make sure that you label this distance down here as your delta, and the distance on either side of your limit is your epsilon. And you don't have to actually write all this down. You can look in the textbook. There's a nice example there. So let's look at another graph. Take a minute and copy this into your notes. So we can I'm going to ask three different questions here. First is, what is the limit of f of x as x approaches 1? So we're going to look at our x value of 1, and we're going to say, what happens to f of x? Remember, f of x, or we might say the function value, is always the y. So when I look for the limit of f of x, I'm looking for the y value that the function approaches as x approaches 1. And we always want to approach from both directions. So as I approach 1 from the left and the right, as I get closer and closer to 1, as I make that delta value smaller and smaller, you can see that if I come in really close to 1, as I look at my y-axis, I am always going to be really close to 2. So my limit of f of x as x approaches 1 is 2. Now in this case, the graph is continuous through this section. There's no breaks or gaps. So the function value of f of 1 is also 2. Sometimes the limit is the actual value of the function. Now let's look at the limit of this function as x approaches 3. So again, if I make my deltas or my epsilons really, really close, I am going to be within the range of 1. So as I come from both sides, they're the same thing, and I'm really close to that 1 value. So although f of 3 does not exist, the limit as x approaches 3 does exist. The last one is the limit of f of x as x approaches 4, and you can see that what happens here is I come from the left, and look at this, and as I come from the right, I'm at two different values, and as I get closer and closer, I'm not approaching any particular number. I'm not narrowing in on the 2 like I did here. So this does not exist. When a limit does not exist, it's often because there is a discontinuity. There are two kinds of discontinuities. The first is a removable discontinuity. If you redefine the function at the point of discontinuity, it would make the function continuous. First, let's talk about continuous. Continuous function is a function that you can draw without lifting up your pen. No holes, no gaps. So a removable discontinuity is one where if you have a hole but plug it up, the function now becomes continuous. So by redefining the function at that point, at that hole that we had originally, by simply redefining this value, we can make the function continuous. So this discontinuity can be removed by simply putting a new value in there. A step discontinuity is one where redefining the function at the point would not make the function continuous. So even if I plug this hole, I still have a jump or a step. So a removable discontinuity is a hole in a graph that is otherwise continuous. A step discontinuity has a jump or a leap. Functions with a removable discontinuity, we can still find the limit at this x value. Even though there's a hole, there is a limit. With a step discontinuity, there is no limit because